Hello and welcome. So today we are going to be deriving some equations, some important formulas that you can be asked anytime you are given a trapezoidal load. You can be asked to derive the equation for the reaction at the support, and you can be asked to derive the shear force equation, and you can also be asked to derive the bending moment equation. All right. So for us to do that, you are going to take note of this, that each time you have a trapezoidal load like this, we have two loads in one. All right. So this load is nothing but we have a uniform distributed load, and we have a uniform varying load. All right. So how do you know that there's a uniform distributed load? If I draw a line from this point down to this point, you are going to see it properly. So let's sketch that out first. All right. So you can see we have a uniformly distributed load. Then we have a what? A varying load. So now the load that is acting on this uniform distributed load is what? W1. While the load that is acting from this trapezoidal load is what? W2. So the load that is acting on this uniform varying load is going to be what? It's going to be W2. That is, from this point to this point is W2. So if you subtract W2 from W1, you are going to get the load that is acting on this what? Uniform varying load. So here we are going to have W2 minus W1. All right. Now, for us to continue with this, we are going to be replacing this support with what? With reaction at B and the reaction at what? At A. All right. So we are going to have reaction at B here. So here we are going to have reaction at A. All right. So, and for us to continue now, we are going to be starting with summation of all forces in the y direction. So we are going to say that the summation of force in the y direction is summation of forces. The y direction is equals to what? 0. All right. So that is sum of upward forces will be equals to what? Sum of what? Downward forces. So we are going to have r subscript A plus r subscript B will be equals to, now we know we have a uniform distributed load, which we are going to convert to a what? To a point load. And we have established that the load that is acting on this uniform distributed load is what? W1. Do you understand? So we are going to convert this W1 to a what? A point load. So how do we do that? We are going to multiply W1 times what? The length. So you can see that this uniform distributed load, it starts from this point and end at this point. So we are going to say W1 multiplied by what? By N. So we are going to have W1N. All right. Plus, all right. So for the uniform varying load, it is not W2 now. It is what? W2 minus what? W1. So for us to convert this uniform varying load to a point load, we are going to be using the area of a what? A triangle. And from the area of the triangle, we know what is going to be what? Half base times height. All right. The base is the length, that is L. Then times the height, which is what? W2 minus what? W1. So we are going to have W2 minus W1 all multiplied by what? L. All right. So we can therefore proceed by writing this in a proper way. You can say that R subscript A plus R subscript B will be equals to W1L plus, so if you if you open the bracket, we are going to have W2L all over 2 minus W1L all over what? 2. All right. So here we can write this to be what? Over 1. So we can therefore say R subscript A plus R subscript B will be equals to, the LCM of 2 and 1 is 2. So we are going to have 2 here. So 1 in 2 is 2. 2 multiplied by W1N is 2 W1N. All right. So 2 in 2 is 1. 1 times W2N, we are going to have plus W2L. Alright. So 2 in 2 is also 1. 1 multiplied by this is what? Minus W1L. Alright. So we are going to say R subscript A plus R subscript B will be equals to W2W1L minus W1L. We are going to have what? W1L plus what? W2L all over what? 2. Alright. So as you can see this, we observe that L is common. We can factor out L. So we can therefore say R subscript A plus R subscript B will be equals to W1 plus W2 into L, everything all over what? 2. So let's call this one equation number 1. Alright. So the next thing we are going to be doing is we are going to be taking our moment. Alright. So we are going to take moment along what? Along B direction. So we are going to say moment, that is the summation of moment about B, will be equals to what? 0. Alright. So now, if we are taking our moment about this point, so we are going to start with RA multiplied by what? Multiplied by L. So we are going to take our upward force to be what? Positive, and our downward force to be what? Negative. If we say upward force, it means the moment that this upward force is creating is going to be what? Positive, while the moment that the downward force is creating is going to be what? Negative. Alright, so here we are going to say that RA multiplied by what? L. So we are going to have R subscript A, L, will be equals to, now, we have converted this our uniform distributed load to a what? To a point load, which is what? W1L. Alright, that W1L is going to act at the center of this beam. So if it's acting at the center of this beam, it means it's going to be what? L over 2 to the left and L over 2 to be what? To the right. So we are going to have W1L multiplied by what? L over 2. So here we are going to say equals to W1L multiplied by L over 2 plus, alright. So now, when we convert this uniform vane load to a point load, we have what? Half into what? W2 minus W1 multiplied by L over what? Over 2. Alright, so now that is going to act at what? At a distance of L over 3 away from the what? From the hypotenuse side. That is from the, if you look at this place, we are going to have a right angle here, right? We are going to have a right angle here. So if we say L over 3 away from here, so here we are going to have L over 3 will probably be at somewhere around here. So L over 3 will be at somewhere around here. Then for you to get the remaining length, you subtract L from L over 3. Then you get the remaining length. I think if I'm not mistaken, L minus L over 3, that is 2L over 3. So that is going, from this point to this point, is going to be 2L over 3. But the distance is going to be what? L is going to be acting at L over 3 away from this place. So now our moment there is going to be 1 all over 2 into W2 minus W1 multiplied by L, then multiplied by L over 3 away from this place. So it's going to be L over 3 multiplied by L all over what? 3. Alright. So if we continue with that, we are going to have our RAL to be equals to L multiplied by L. That is W1 L square all over what? All over 2 plus, here we are going to have L multiplied by L is L square. So if you use L square to clear the bracket, we are going to have W2 L square minus W1 L square, everything all over what? All over 6. 2 times 3 is 6. Alright. So again, we can collect the LCM. Alright. So we can say that R subscript AL will be equals to, the LCM of 2 and 6 is what? 6. 2 in 6 is 3. 3 multiplied by this is what? 3W1 L square plus 6 in 6 is 1. 1 multiplied by everything we have here is going to be W2 L square minus W1 L square. Alright. So now the next thing is 3W1 L square minus W1 L square. That is what? 2W1 L square. So we are going to have R subscript AL will be equals to 2W1 L square. Then we are going to be having plus W2 L square. All right. All over what? All over 6. All right. So if you look at this now, we can factor out L square. So we are going to have RAL to be equals to 2W1 plus W2 all into what? L square all over what? 6. And if you look at this L here will go with one L here. So we are going to have our reaction at A to be equals to what? 2W1 plus W2 all over what? 6 into what? Into L. Alright. So this is the reaction at A. Alright. So for us to get the reaction at B now, we are going to substitute this into what? Into our equation number 1. So you know we already have RA plus RB to be equals to this. So if we substitute for RA here, we are going to have, we said, let's call this one our equation number 2. So from equation 1, we have RA plus RB to be equals to W1 plus W2 into what? Into L all over what? All over 2. Right? Alright. So for us to make RB the subject here, we are going to take RA to the other side. So we are going to have RB to be equals to W1 plus W2 into L all over 2 minus RB. And RB is what? RB is 2W1 plus W2 all over what? All over 2 into what? Into L. Alright. So now, since they are having the same, oh sorry, this one is 6. This one is 6. Alright. So now the next thing we are going to do is we are going to find the LCM of 2 and 6, which is what? 6. So we are going to say RB will be equals to, the LCM of 2 and 6 is 6. So 2 in 6 is 3. 3 multiplied by everything here. So it's going to be, you can just open the bracket directly like that. So 3 multiplied by this multiplied by L is 3W1 L plus 3W2 L minus 6 in 6 is 1. So minus 1 we multiply everything with L. So we are going to have minus 2W1 L then minus W2 L. Alright. So everything over 6. Now 3W1L minus 2W1L is going to give us what? 1W1N. So we are going to have our reaction at B to be equals to W1L plus 3W2L minus W2L. That is what? 2W2L all over what? All over 6. We can therefore factor out L now. If we factor out L, it means that we can write this our equation to be equals to W1 plus 2W2L all over 6, everything multiplied by what? L. So now this is going to be the reaction at B, and this is the reaction at what? At A. Alright, so we are done with the reaction at A and then the reaction at B. So you can see the reaction at A is 2W1 plus W2 into L all over 6. While the reaction at B is W1 plus what? 2W2 all over 6 multiplied by what? By L. Alright. So we are going to be deriving the shear force equation now. So I'm going to clean this side. Alright, so we are going to be deriving the shear force equation now. So shear force equation. Alright, so for us to do this, for us to derive the shear force equation, I'm going to denote it with this. Alright, so for us to derive the shear force equation, we are going to be sectioning this beam. We are going to, you can decide to section it at this side, You can decide to section it at this side, but I just prefer sectioning it at this side. Alright. So we are going to call this place W subscript S. Alright. So the distance from this point to this point is S. Let's call this place S. Alright. Alright. So now for us to do this, you are going to take note of this. That from this point here to this point is what? WS. We don't know what WS is. While from this point to this point, we have it to be what? W1. Alright. So now, for us to derive the equation here, we are going to say the shear force equation is going to be equals to, now, if you section this beam here, it means that we are taking away all these parts. You understand? So now we are just going to focus on this part only. All right. So now the shear force equation here is going to be equals to RA. Then we have a trapezoidal load here. We have a trapezoidal load. All right. Because even if you section it here, you still have a trapezium. If you section it here, you have a trapezium. Is that clear? All right. So now if you stand at this point where we section it, we are going to observe that we have a trapezoidal load. All right. So now the shear force equation now is going to be equals to this RA minus what? Minus the area of what? Of the trapezium. All right. So this is going to be equals to RA minus half into, we know that the formula for a trapezium is what? Half into what? A plus B, right? A plus B multiplied by what? Times height. All right. That is the sum of the parallel side. All right. So now if you look at this, we have here to be what? We have here to be what? W1, and we have here to be what? WS. So we are going to have this to be what? W1 plus WS multiplied by what? The height. So the height from this point to this point is what? S. So it's going to be S. All right. But the question now is, what is WS? We don't know what WS is. We know what our ROS is, and we know what our W1 is, but we don't know what our WS is. We don't also know what our S is. All right. So for us to analyze for that, what we are going to do is we are going to be using the condition of a similar triangle. All right. If you look at this, we have these full triangles. That is this, and this part. And if you look at this, we have from this point to this point, we have another triangle here. Please take note of this. So we have this bigger triangle, and we have another smaller triangle here. All right. So we are going to be doing a similar triangle to do that. All right. If you look at this, from this point to this point, we don't know it, but we know that from this point to this point is WS. And then we also know that from this point to this point is W1. So this point now is going to be what? WS minus what? W1. Only for this point only. So this place is going to be WS minus W1. I don't know if you can see this. All right, minus W1. All right. So this point is WS minus W1. And this point only is going to be what? It's going to be W2 minus what? Minus W1. All right. So, and then the length of this smaller triangle is what? WS. While the length of this bigger triangle is what? L. All right. So from the similarity of a two triangle, WS minus W1, W subscript S minus W1 all over S will be equals to this, all over this will be equals to W2 minus W1 all over what? All over L. All right. So if we make WS the subject here, WS will be equals to, if you cross multiply, S will multiply everything that we have here. If you bring this one here, you are going to have it as positive. So you are going to have W1 plus W2 minus W1 all over what? L. Multiply by what? Multiply by S. So this is what our WS is. All right. So now we can therefore substitute let's call this equation number 3. All right, let's call this equation star, or let's call this equation 3, and let's call this equation 4. All right, so now we can therefore substitute equation 4 into what? Equation 3. All right, so we can therefore say our shear force equation now. Our shear force equation will be equals to RA minus half into W1 plus WS, which is everything that we have here. It's going to be W1 plus W2 minus W1 all over L multiplied by W1, then multiply into what? S, and close your bracket, then multiply by what? Multiply by S. All right, so we can open that bracket. We are going to have shear force equation to be equals to RA minus W1 plus W1, that is half into 2 W1 plus, so S, okay, this S is for everything. Let's just take it one after the other. So this is going to be W2 minus W1 all over L into S into S. All right, so now we can open the bracket now. This is equals to RA minus half times half times 2 W1 is going to give us what? Minus W1, and multiply by S. We are multiplying this bracket with half and with what? With S. So if we do that, we are going to have half multiplied by W1 multiplied by S, which is going to give us what? W1S. All right, so if you multiply half by what we have here and by S, we are going to have minus half into W2 minus W1 into S squared all over what? All over L. All right, so now this will be equals to R subscript A minus WS. Then if you open this bracket now, we are going to have this to be what? We are going to have this to be 2 times L, that is what? 2L, right? So we are going to have, and this times this, we are going to have minus into W2 minus W1 S square all over what? All over 2L. All right, now we can therefore substitute for our RA here. What is our RA? Our RA is what? 2W1 plus W2 into L all over 6. So we are going to say 2W1 plus W2 into L all over what? All over 6 minus WS minus W2 minus W1 S square all over what? All over 2L. All right. All right. So here is our shear force equation. Here's our shear force equation. But in some textbooks, you can see your shear force equation like this. I just decide to simplify further. You can leave your shear force equation as this, and then you can also leave it as this. You can just go with the one that will be easier for you to memorize, in case you want to memorize all the equation. All right, but there's no need for you to memorize. Just learn the processes. All right, so now the next thing we are going to be looking is our bending moment equation. All right, so we can denote that with M subscript S. All right, so this is very simple. You just need to do this to this equation. You know, here we have our RA. This is our RA, and here's our RA here, and this is the section that we are considering. So if we consider this section, for us to get the moment, we are just going to say RA multiplied by S, and our RA is this. So we are just going to multiply this with what? With S. So you can write it in this way. You can say RA multiplied by S, then minus, now this WS. Now we know that this is supposed to be W1, not WS. Supposed to be W1S. Alright. So this W1S is our uniform distributed load that is converted to a point load. So if you convert that to a point load, if you want to convert this uniform distributed load here to a point load, it's going to be W1S. So, and which is going to act at what? At the center, that is x over 2 to the left, x over 2 to the right. So if you do that, we are going to take this is going to be W1x multiplied by x over 2. Alright, minus, alright, and this one too, if you convert this uniform bearing load here to your point load, this is what you are going to have. You are going to have what is here. So for this is the load himself. So for you to get the point, it's going to be what? L over 3 away from your right angle. So you just need to multiply this force here by what? By x over what? Over 3. So here we are going to have this to be W2 minus W1 into x over 3 all over 2L multiplied by x all over what? 3. So you can decide to leave it like this, or you can just say s times s, that is s squared. So you can have it as W1 s squared over 2. Then this is going to be s cubed, that is W2 minus W1 into s cubed all over what? 3 times 2L, that is 6L. So this is how to derive the equation for the reaction of the support, and the shear force equation, and then the bending moment equation. So we are going to be using this formula to solve questions, and we are also going to be solving a question on this, still following the same processes. So stay tuned. Thanks.